So now that I have my tables, let's look at arsenic hydrogen bond. So to figure out the type of bond, so we're talking, is it nonpolar covalent or polar covalent? We are going to look up the electronegativity values on our table, subtract arsenic from hydrogen, and then compare it to this table here. So if it's 0.5 or less, it's nonpolar. If it's 0.5 to 1.9, it's going to be a polar covalent bond. So AS is 2.18, and then hydrogen is 2.20. So they're very close to each other. They're almost exactly the same. So when I subtract those, remember it's absolute value, so you're not going to get a negative, I would get 0.02. So very small, right? So this is going to be a nonpolar bond because it is less than 0.5. So looking at number 14, we're getting into some chemical formulas. So predict the chemical formula when rubidium combines with a carbonate ion. So to figure this out, notice I said ion, so we know this is an ionic compound. We would also be able to tell that because rubidium is a metal, and metals are involved in ionic compounds. So I would look up rubidium on the periodic table and write its symbol, Rb. Okay? I would also write its charge. What is its most probable ion? So based off of where it is on the periodic table, I can figure that out. Rubidium is an alkali metal in group 1, so those all form plus ones. They lose one electron to form a plus one ion. Now for the carbonate ion, notice that ATE ending, carbonate, that means it's a polyatomic. So you would go to your polyatomic tables, find the carbonate ion, which is CO3 with a 2 minus, and write its charge. So to figure out what this chemical formula is going to look like, I need it to be neutral. Right now it's not, because I have a +1 charge here and a -2 charge there. So what I need to do is I need to add another rubidium. Now I have a +2 on the cation side, and that will cancel out my -2 on the anion side. So that's 2 rubidiums and 1 carbonate. So my chemical formula color is going to be Rb2CO3. Now for number 15, this is just asking about bond types. So a blank bond is a bond where atoms share electrons unequally. Okay, so they're sharing electrons, so I know it's going to be a covalent bond. But notice it also says they're sharing them unequally. So unequal is that polar covalent, because that occurs when we have one atom in the bond much more electronegative than the other, meaning that it wants those electrons more, so it's not going to share those electrons equally. It's going to have a partially negative charge on it. So that would be polar covalent. Number 16 is asking what group or family does cesium belong in? So cesium is in group 1. It's right underneath rubidium who we just looked at. So this would be alkali metal. Group 1, with the exception of hydrogen, are the alkali metals. Let's look at number 17 and name some compounds. So P2Br4, so in order to name it, you need to know what type it is. Is it covalent? Is it ionic? So covalent is nonmetal with a nonmetal, or a metalloid with a nonmetal. Ionic, it's going to be a metal with a nonmetal, or a metal with a polyatomic, or 2 polyatomics together. Those are all ionic ones. So look at what you have because the rules differ. So here we have phosphorus and bromine. They are both nonmetals. They're both to the right of the zigzag line. So that means this is going to be a covalent compound. And covalent compounds, we use prefixes. So we use the prefixes to identify how many of each atom. So these subscripts here. So there are 2 phosphorus, So that would be diphosphorus. There are 4 bromines. Now, for the bromine portion, the second element present in the chemical formula, we have an IDE ending. So we're going to start with a prefix since it's covalent and write tetra. But instead of bromine, we're going to write bromide, IDE ending. The next one, PD, and then notice there's parentheses with the OH and a 4 after it. So whenever you see parentheses in a chemical formula, that's most likely there's a polyatomic there. Okay, and if there's a polyatomic, that tells you it's ionic, because those are ions, charged components. Now, looking up PD on the periodic table, that's palladium, that's a transition metal. So with these ones, when you have a transition metal, you need to use a Roman numeral to indicate what charge, because remember, transition metals can have variable charges, so we're going to need to use a Roman numeral to indicate what ion we're looking at. So these ones are a little more difficult. What you need to do is you're going to write the element. I'm going to put a question mark there because I don't know what the charge is just by looking at it, right? But to figure out the charge, you look at what it's attached to. And it's attached to OH, the hydroxide ion. And when I look that up on my polyatomic tables, it tells me the hydroxide ion has a -1 charge. Okay? But notice, there's 4 of them. So I'm going to draw 4. 1, 2, 3, 4. So my total negative on the anion side is -4 because I have 4 of those ions. So in order for this compound to be neutral, I need to have a +4 on the cation side. Well, I only have 1 palladium, so that means that entire +4 charge is going on that palladium. So I have the palladium 4 ion is what I'm dealing with. So when I name it, no prefixes because it's ionic, so I'm going to do palladium, Roman numeral 4, and then OH, that's polyatomic, and I look on the polyatomic table and write it exactly how it's written on there, hydroxide. So palladium 4 hydroxide is the correct name for that guy. There's one more, and that's this K2S. So for this one, looking at it, it's ionic because I have a metal, potassium, with a non-metal, sulfur. Okay? Now, I don't use prefixes because it's ionic. Since my metal is a main group metal this time and not a transition metal, I do not use Roman numerals. So you only use Roman numerals for transition metals. So I go look up K, and that is potassium. Then I name the second half, the sulfur, and I don't use prefixes, but I am still going to do that IDE ending, and it's going to become sulfide. So potassium sulfide is the correct name for that guy. All right, let's move on to Lewis structures. So number 18 is asking how many valence electrons contribute to the Lewis structure of PF3. So, number 19 is then asking us to draw the Lewis structure. So let's just go through all the steps. Phosphorus is going to be my central atom. I'm going to have the 3 fluorines around it. Before I continue on with drawing that, I need to know my valence electrons. So to do that, I make a list of the atoms present, phosphorus and fluorine. I write the number of atoms of each, and multiply that by the valence electrons from the periodic table. So I have 1 phosphorus. Looking at where phosphorus is on the periodic table, it's in group 15, so it has 5 valence electrons. For the fluorines, there are 3 atoms. So how do I know that? We're looking at the subscripts. Okay, so it says 3 fluorines. For valence electrons, there is 7. Because it's a halogen in group 17. So multiplying that out, I get 21 plus 5 for a total of 26 electrons. So that's the answer to number 18, 26 valence electrons. Now to draw the Lewis structure, we're going to take those 26 valence electrons and make the terminal atoms happy first. So to do this single bond counts as 2 electrons. So we need to add 6 more to each fluorine so they have a full octet, a total of 8. Okay, so 8, 8, 8. They're all happy. Okay, how many have I used? Well, 8 times 3 is 24. So I've used 24 of my 26, so I have 2 electrons left. Where would I put them? Well, now we focus on the central atom. So phosphorus, each of these single bonds is worth 2 electrons, so phosphorus has 2, 4, 6 electrons. Okay, but he wants 8. Well, I have an extra pair that I can put on him. So now he has 8. So that is the correct Lewis structure. Now, number 19 is saying the individual bonds for PF3 are blank and the molecule is blank. So what we're looking for here is polar or nonpolar. So to figure out if the bonds themselves are polar, so we're talking this bond here is a phosphorus fluorine bond, polar or not. You're going to use your electronegativity tables. You are going to subtract their electronegativities from each other and see what range they fall in. So phosphorus is 2.19 for its electronegativity. Fluorine is 3.98. I'm not going to be able to do that in my head. But I know that it is over 1. So it's going to be polar covalent bond. So the bond itself is polar. Okay, but what about the molecule as a whole? So now that we have the Lewis structure, the molecule as a whole, is the molecule itself polar? Well, for that, you look at those rules. For nonpolar molecules, we said no lone pairs on the central atom, and then all terminal atoms the same, or if there's carbon and hydrogen only. For polar molecules as a whole, we said if there is one or more lone pair on the central atom, it would be polar. We have a lone pair on the central atom. Okay, so this guy is polar as well. So not only are the bonds themselves polar, but the molecule as a whole is also polar. So when you're approaching a problem like that, break it up, okay? Find just that bond and see, is that bond polar based off its electronegativities? Then bring in the whole picture, look at the central atom. Is there a lone pair on it? If there's not, are all terminal atoms the same? And go from there. Okay, you can also do that dipole moment that we talked about as well. That would work. Just for fun, let's name what type of molecular geometry this guy has. So for molecular geometry, you're looking at how many things around the central atom. And we have 4 total things, right? 1, 2, 3, and then this lone pair also counts as a thing. So we have 4 total things. So we're at our 4 comma. And what comes after that comma is how many of those 4 things are lone pairs. So we're looking at 4 comma 1. So this guy would be a trigonal pyramidal. Pyramidal, can't spell. Bond angles less than 109.5, I believe. All right, let's move on to number 20. What type of bond is present in the molecule carbon monoxide? I think I actually did that last class. But to figure that out, when I say what type, single, double, triple, what type of bond? So to do that, you would need to go through all the steps of the Lewis structure. So number of valence electrons. We have 1 carbon atom, we have one oxygen atom. Carbon has 4 valence electrons, oxygen has 6, for a total of 10. There is no terminal atom, so just pick one to make happy. Okay, I'll pick oxygen, so I'm going to give him 6 more since he already has 2 for a total of 8. So now I've used 2, 4, 6, 8, but I have 10. So I'm going to take that last pair I have and put on carbon. Now notice, oxygen's happy, carbon is not. So what we need to do is we need to take an electron pair from oxygen and go to make a double bond. I do that there, that can be confusing. But now, look at carbon, he's got 2, and then 4, 6. So he's still not happy. So oxygen's going to take another pair. So now we have a triple bond, 1 lone pair on oxygen and 1 lone pair on carbon. So carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. So both are happy. And we've used a total of 10. So we didn't go over our valence electron count. So it would be a triple bond. It's also a polar bond if you want to do the calculation. All right, number 21. Metals tend to gain or lose electrons to form an ion. So remember, metals form cations. They form cations, positive charges, because they are losing negatively charged electrons. So 21 would be lose electrons. Metals tend to lose. Number 22, more chemical formulas. So we named some guys. And so this last question gives us names, and we're going to come up with the chemical formula. So we have vanadium nitrite. So notice the Roman numeral. This is going to be a transition metal. Since it's a transition metal, we need to write the ions with the charges, and then we can either do the crisscross method or the stacking, where we see how many more positives or negatives we need to make a neutral. So vanadium is a V on the periodic table. What is its charge? That's what the Roman numeral's for. It's going to be a +4 because of that Roman numeral 4. I know it's plus because metals, we just said, lose electrons to form a positive charge. Now nitrite, I-T-E, that tells me it's a polyatomic. So I'm going to go to my polyatomic table, and nitrite, hopefully it's on here, NO2. So it's NO2 with a -1 charge. So doing the crisscross method would tell me I need 4 nitrites and 1 vanadium. So that would give me vanadium and then NO2. And I just said I needed 4 of them, right? But since the polyatomic, make sure you put parentheses and then the 4 on the outside of the parentheses. Because what we're saying here is we need 4 NO3s. If we forget the parentheses, it's going to look like we have 24 oxygens, and we don't want that. Okay? All right. Potassium sulfide. That's funny because I think we named that one from the chemical formula earlier. So potassium, this is a metal and a nonmetal. This is an ionic compound once again. Whenever you're approaching the ionic compound and you're trying to figure out what the chemical formula is, you have to write the ions. What are the ions involved? So potassium is K, sulfide is just sulfur with an S. But I need to know the charges. So what is the most probable ion for potassium? It's an alkali metal. So alkali metals like to form a +1. Sulfur is in group 16. It likes to form a -2 charge. So once again, you can do the crisscross method. The other way is looking at the charges, trying to get them neutral. Looking at them, I see that I need to add another positive ion. That will give me a total of +2 on the cation side and a total of -2 on the anion side. So I need 2 potassiums, K2, and 1 sulfur. So this would be the correct formula for potassium sulfide. Now the last one is trioxygen difluoride. So notice the prefixes tells me it is a covalent compound. So you don't need charges. There are no charges in covalent because they're sharing electrons. So for this one, you would write the two elements involved. So trioxygen, oxygen being O, and then difluoride, and fluorine being F. Now to figure out the subscripts for these, use the prefixes. So trioxygen, so tri means 3, difluoride, di meaning 2. So there's our chemical formula for trioxygen difluoride. And that wraps up the review. So you have until tomorrow night at midnight to take the exam. On Thursday and Friday, we'll be starting Chapter 4. And you do have a homework assignment due on Sunday for Chapter 4, Part 1 of Chapter 4. So let me know if you have any questions, if you want to do a Zoom meet or anything. I know I had to cancel class yesterday due to a migraine. So I'm here to help even into the nighttime. So let me know.